the previous tutorial, we did a quick introduction to machine learning and what you need to know for you to be able to develop TinyML applications. In this tutorial, I'll be giving you a high-level introduction to embedded systems and electronics. And towards the end of this tutorial, we're going to be going into details about the board that we'll be using throughout this tutorial series, which is the Arduino Nano 3B license and the RP2040 board. This tutorial is divided into three parts. The first one is core electronics, second one is embedded system design, and the third one is introduction to Arduino Nano 3B license and the RP2040 board. Under core electronics, we'll be looking at circuit fundamentals. This involves voltage, current, resistance, Ohm's law, power, and Kirchhoff's law. You also get to learn more about resistors, capacitors, and diodes. Under embedded system design, we are going to be looking at microcontrollers and microprocessors. We also do a quick comparison of these two and how they differ. We are going to be looking at architectures of microcontrollers. We look at I/O ports, memory, we look at interrupts, and also look at timers. We also look at sensors and actuators. And finally, we look at communication protocols. We'll be looking at wired communication and also wireless communication. We'll be talking about SPI, I2C, UART, Bluetooth, and Zigbee. And finally, we'll be going into the full details about the boards that we'll be using throughout this tutorial series. We'll be looking at the Arduino Nano 3B license board and the RP2040 board. We'll be looking at the comparison of these two boards and also how they differ. We'll look at the technical details of these two boards, and we'll also look at some of the sensors that this board comes with. So, without further ado, let's get started. As I mentioned earlier, we are going to be looking at three different parts, and we are going to be starting with circuit fundamentals, which is the fundamental building blocks of electronics. You agree with me that there's no other way to start than by looking at the principle of voltage, current, and resistance. And then I'm going to be using a simple water analogy to explain the principle of voltage and current. I have a battery here, which is a voltage source and a single part for the flow of current, and an electric bulb which comes on when current passes through the circuit. Think of voltage as electrical pressure. It is the force that pushes electron through a circuit and is measured in volts. Now, same thing applicable to current. So this is simply the flow of electron or charge through a circuit. Think of it like water flowing through a pipe. It measures in ampere. And basically, current is what makes an electric circuit to work. It is simply the flow of electric charge across surface of a conductor in a given time. So, we can also define current as Q over T. And this means the amount of charge flowing through a particular conductor with time. So, we know that we measured our voltage in V, which is volts, and we measure current in A, which is amperes. So how do you know whenever you see a current or a voltage in a circuit? There are different symbols for representing voltage source, and there are different symbols for representing current or current source. So one very common symbol is the symbol for battery, which is simply something of this nature. So the small side indicates the negative side, and the long length represents the positive side. We'll be looking more into current source in our circuits. We'll be looking more into voltage source and batteries and AC source. So let's just hold on at this level for now, and then we'll look at the concept of resistance. Everything will have been easy if you have our voltage and our current, we have our wires, we have our electric bulb, and we have our battery. You can just power up everything and then it starts working. But then we have resistance, which is simply the resistance to the flow of current. So I find this representation online, and it's one of the best way to represent the concept of resistance. We have voltage, which is basically trying to push current in the circuit, but resistance is anything that is hindering the flow of current in that circuit. So we can see that resistance slows down the current. It's like putting a kink in a hose pipe to reduce water flow, and it measures in ohms. So our resistance is measured in ohms, and whenever you see this symbol in the circuit, it simply means resistance. So whenever you see this symbol, we're looking at resistance. So basically in a circuit, you are going to be seeing a lot of voltage source, a lot of resistance, and symbol for battery. After learning about voltage, current, and resistance, the next important thing we need to look at is the concept of Ohm's law. Ohm's law is basically the law that ties these three things together. I will say that Ohm's law states that the electric current through a conductor between 2 points is directly proportional to the voltage across the 2 points. What does this mean? You can see that, firstly, if you are going to write out the equation, we have that voltage equal to the current multiplied by the resistance. Now, how can we represent it, and what does this mean for us in a circuit? If I have an example, a 9-volt battery connected to a 100 ohm resistor gives a current of 0.09 amps. What does it really mean? We have a 9-volt battery, we have a load. It can be a resistor, a LED load, or anything that is 100 ohms. And with this, we can say that the current passing through the circuit is simply 0.09. So we use Ohm's law to get these derivations. We have our voltage source, which is 9 volts. We have voltage is equal to current times resistance. So 9 equals to the current, which is what we are looking for, I, multiplied by resistance, which is 100 ohms. So we can see that I equals to 9 divided by 100, and this equals 0.09 amps. So with Ohm's law, we're able to find the relationship between the voltage, current, and resistance. This is a very important law for us to know before diving into electronics. We're going to be doing a lot of, though we're not going to be doing much of calculations, but it's very important for you to have this formula handy and know how to calculate the current or the voltage or even the resistance flowing through the circuit. Another important thing you have to take note of is power. Power is basically putting electricity to work. We can define power as the rate at which electrical energy is used. The calculation of power is very important when we are designing our circuits, because we are going to be basing our current source, our voltage source, based on the power that we need in our circuit. If we are going to choose a power source, a voltage source for our circuit, or a battery for our circuit, we need to accurately calculate the power that our current desires and then give it the right power supply. So how do we calculate power? We simply put that power equal to voltage times current, and power is usually measured in watts. So, for example, if you have a resistor, or we have, let's say, a sensor to be used in our circuit, we have sensor A. The voltage being drawn is 3.3 volts, and the current that the sensor draws is 0.25 amps. So to calculate the power required by that particular sensor, we can simply say power equal to voltage, which is 3.3 volts multiplied by 0.25 amps. So whatever we have here will be the power that will be drawn by that particular sensor. So the battery source that we are selecting, the voltage source we are selecting, must be able to give that amount of power, unless we won't be able to power that particular sensor. So that's one very shallow analysis of how power is very important and how the calculation of power is very important while designing our circuits. Before moving on, it's important for us to know the difference between energy and power. Sometimes we interchange the words power and energy because we think they are related, but in actual sense, they refer to different physical quantities. In fact, we can say that energy is the capacity for doing work, for example, using a force to move an object, while power is the rate of consuming energy. So in practical terms, power tells us how fast we drain the energy. So high power simply implies a faster battery discharge. So power and energy, they are related to voltage and current through the following formula, which is the formula we looked at in the previous slide, which is P equal to I V. So we should know the difference between power and energy. What we are majorly concerned about throughout our circuits design is going to be power, not much of the energy. Most of our calculation will be power calculation, not energy calculation. Before rounding off on basic electronics, there are two other laws we need to look at, and these are generally referred to as Kirchhoff's laws. And these are the traffic rules of circuits. So we have the Kirchhoff's current law and the Kirchhoff's voltage law. So what is the current law and what is the voltage law? We say that for Kirchhoff's current law, the current entering a junction where wires meet must equal current leaving. So it's like water in a pipe, what goes in must come out. What we have is that if you have a wire coming in this direction and we have to branch out, probably to do some work, and then branch out to do some other work. So we have a current flowing in, which is current I, and when it branches out, we have this place to I1 and I2. So what Kirchhoff's current law states that I must be equal to I1 plus I2. So that's Kirchhoff's current law. And then we also have Kirchhoff's voltage law, which is that all voltage around a closed loop in a circuit must add up to 0. So think of it like a hike where you end up at the same height that you started. So what this means is that if you have closed loop, you have a resistor, you have another resistor in the circuit, and we have a voltage source. So this is the voltage of resistance A, voltage of resistance B, and we have a voltage A. So what Kirchhoff's current law states is that the addition of all these currents must be equal to 0. So V plus VA plus VB must be equal to 0. So that's Kirchhoff's voltage law. It's very important to know these two laws while designing your circuit. So you have to know that the current entry a particular loop must be equal to the current leaving the loop, and the sum of all the currents of all the voltage in a closed loop must always be equal to 0. Now, let's do a simple design calculation that relates to power. Let's say we are using Arduino Nano 33BL license. They are basic and there are some specifications. If you check the data sheet online, we know that the DC current per high pins is 10 milliamps. So that's the current that can pass through the pins of the Arduino Nano 33BL license. That's the input and output pins is 10 milliamps. So if you have a component that takes a lot of current, you have to power it from external power supply. For example, if you are using an electric motor in your circuit, it's not advisable you power it using the pin of the Arduino Nano 33BL license. You just power it from an external power supply. And the board, which is Arduino Nano 33BL license, draws 25 milliamps in sleep mode. You can always check the description below for the specifications of the Nano 33BL license. Now, we have a battery for our circuit, and the battery is rated 500 milliamp hour. And based on what we are designing, we have Nano 33BL license, we have the Nano 33, which, let's say in sleep mode, it takes 25 milliamps. So we have other components in our circuits, and they take a total of 300 milliamps. So these are the power rating. We've already saw how we calculate power. P is simply equal to I times V, current times voltage. So after doing our calculation, we're able to get that Nano 33BL license is drawing 25 milliamps in sleep mode, and other circuits that we have, other sensors we have, other components that we have in our circuits is drawing 300 milliamps. And we have a battery of 500 milliamp hour. So what does this imply, and what is this telling us? So we can simply say that we're able to run this circuit for a total of, we know that total power in the circuit is 300 plus 25, so which is 325 milliamp hour. So to get the number of time that our battery is able to last for, so we simply say time equal to 500, which is our battery capacity, divided by 325. And then I have 1.5 hours. So this implies that we're able to run this circuit using this battery for just 1.5 hours. So the better battery you select, let's say you get another battery of 5,000 milliamp hour. So this is promising you more hours of run without the battery running down. So you have to know how to do this calculation so that you know how last or how long your battery will be able to sustain the circuit for. So that's basically all as regarding review of basic electronics. There are a lot more to electronics that we won't be able to cover in just 15 minutes tutorial. You can always check other electronics books or electronics videos online to learn more about basic electronics. Now we're going to be reviewing some concept of embedded system design and look at some core things that we need to know before you can start designing our TinyML applications. The first thing we need to define is microcontrollers, and this will be the brains of all embedded system devices. So the question is, what is a microcontroller? So we say that a microcontroller is a small self-contained computer on a chip. So you can think of it as the heart of many electronic devices. So it contains a lot of other peripherals that we're going to be looking at. And first we have to know that most of the things we are going to be dealing with in TinyML is simply going to be on microcontrollers. There are other categories that we call microprocessors, and towards the end we're going to be looking at the difference between microprocessor and a microcontroller. But for now, let's take a deeper look into the concept of microcontrollers. Now, what are the key components of microcontrollers? The first one we have is the CPU, and it's simply the processor that executes the code. One thing you should know that in the microcontroller, all the necessary components are in a single chip, unlike a microprocessor that we're going to be looking at later. Now, another thing we have inside the microcontroller is the memory. So we have the RAM, which is the temporary storage for variables and data, and then we have the ROM, which stores the microcontroller's program. So we also have the peripherals inside our microcontroller. We have I/O ports. This can be connected to sensors, actuators, and other devices. We also have timers that are helping us to keep track of things, and we have interrupt controllers for handling interrupts. So this whole combination is referred to as a microcontroller, and think of it as it's just a small self-contained computer on a chip. You see, we have our CPU on board, we have the RAM on board, we have the ROM on board, and we have all the peripherals also on board. So that's basically what divides the concept of a microcontroller. Now, before we look at the comparison of microcontroller and a microprocessor, there are different common architectures of microcontrollers out there. We have the AVR type, which are popular in orbit. These are the type of microcontroller we have in Arduino, we have in some Uno and some AVR chips. So we also have PIC. So PIC are basically used in industries, and they are known for low power consumption. And lastly, we have ARM. ARM is very common and very powerful and versatile, and is found in our smartphones and in more complex devices. So, though our focus will be on microcontrollers, as I mentioned earlier, we just do a quick comparison with microprocessors. One thing we often do is that we often confuse microcontrollers with microprocessors, but they refer to different devices. In contrast to a microprocessor integrates only the processor on a chip. For example, what we are saying now is that we have a microprocessor and we have a microcontroller. You can see for a microprocessor, we only have this is the chip, and the only thing we have on the chip is the CPU. So requiring external connections to a memory system. So we have to get memory externally. We have to get SSD, flash, or ROM externally, just like our computer. We have our CPU on board, and then we have to put in our RAM. Externally, you have to put in our ROM, which is our hard disk or SSD externally. Another component for us to have a fully operating computer. So for a microprocessor, for a microcontroller, this is not like that. We have the CPU on board, we have the RAM, we have the ROM, and then you also have all those other peripherals in a single chip. So for a microcontroller, the tasks are single purpose and repetitive. We can only do one thing at a time, and then we can do that thing continuously for as long as we want. So there's time constraints, there's physical size constraint, and then there's low power constraint also for microcontrollers. But the microprocessor is dynamic. It's for general purpose computing, it's for generic computing, and it can do heavy duty calculations and a whole lot of processing compared to a microcontroller. A very basic example of this is a Raspberry Pi. Raspberry Pi is a microprocessor, while an Arduino is a microcontroller. Another important concept in the world of microcontrollers is memory. So this is basically where the program data and every other thing that we're doing as regarding code lives. So we both have RAM and then we have ROM. So there are different types to this that you can always check online and learn more about how our Arduino handles RAM and ROM. So just like a normal RAM that we have in our computer, it's volatile. It's whenever you off the computer, the data on the RAM will disappear. It's used for variables and it's used for the program stack. But for ROM is like our hard disk. It's non-volatile. It retains our data. So there are different types of ROM. So we have the flash ROM, we have heap ROM. So this can be electrically erased and rewritten. So there are basically two types. We also have SRAM, and there are different other form of RAMs that we have. We have EEPROM, we have PROM, and some other ones. So you can always come on how our memory works and how Arduino handles RAM and ROM for it to process the code, any code that we are writing to it. All our microcontroller board give us access to I/O ports. So these are basically the pins that we use to interact with the world. So that's the difference between our computers and other microprocessors like Raspberry Pi. Our computers does not have pins that we can plug in a LED or plug in some other things. But for a Raspberry Pi, it gives us this I/O port that we can talk to the world, interface with other sensors. So we have pins, which are basically the connecting points. We use this for physical pins. These are like physical pins on the microcontroller. We also have digital I/O. So these are digital inputs and outputs. We can read or write. We can write a line high. We can write it low for it to on an LED. We can use it for buttons. can use to control anything. We also have analog. We can send in pulse width modulation. We can read an analog sensor using analog input and output pins on the microcontroller. And lastly, one important concept that we also need to look at is communication protocols, because we need to communicate between our devices, sometimes over to the internet or with other devices. And there are different means of communicating with our microcontroller board. For example, we have some kind of sensors that might need to interface with our microcontroller. Sometimes we might need to send data from our microcontroller to some other parts of the world through via the internet or via other means. So we have different wired protocols. So this involves physically connecting our board with the sensor. So we have UART, which means Universal Asynchronous Receiver Transmitter. This one we are using TX and RX. So it's very simple, just two wire transmit and receive. So it is like point to point. It's very common. It's very common for debugging. Whenever you want to connect our device also to the computer, we use the UART principle. We have the protocol. So we also have I2C, which is called inter-integrated circuit. Also, only two wire is required in I2C, just the data line and the clock line. So we can have multiple devices on the same block. So each block is going to have its own address. Though there are a lot of principles to how I2C work, the concept of delay, the concept of slave and master, but we can also look at those ones later and then learn more about I2C. So it's very common sensors, common protocols you see on most of the sensors these days. So it's used in sensors, EEPROMs, and some displays. And lastly, we have SPI. SPI means serial peripheral interface. So in SPI, we are using 4 lines. So compared to I2C, that we are using 2 lines. So we have the clock line, we have the data in, we have the data out, and we have the slave select. It's faster than I2C. It is full duplex. So it can send and receive at the same time. This is one advantage of SPI over I2C. So you can have one master and multiple slaves. So the master can send multiple slaves at the same time without any interference. So it's very common when it comes to use with SD card, displays, and high-speed data transfer. So we also have wireless protocol. These are protocols whereby we do not require wire between our device and the sensors, or between our device and the other microcontrollers that we have. So you can use the Bluetooth protocol. So this works in a short range, like device to device. We have also Bluetooth low energy, which is BLE, for reduced power consumption. So it's very common in headphones, speakers, wearables, and also data exchange. We also have Zigbee. Zigbee is like a mesh network. So like devices relay data for extended range. It's low power also, just like Bluetooth. It's ideal for sensor network. Also, it's for common communication, home automation, industrial monitoring. Another one that I didn't add here is RF. So we also have RF, which is basically used for communication between two devices. The two devices have to have RF protocol enabled before they can communicate, and it's very efficient and it's very fast, and they can travel wider and longer than Bluetooth. So now, how do you not choose a protocol for you to use? For example, if you have some sensors that can communicate over different protocols, which one are you going to use? The first thing you have to consider is speed. So how much data needs to be transferred? You also have to consider the number of devices that are available. So another thing you have to consider is reliability, how reliable it is. Should you go for a Bluetooth connection or you go for a wired connection? Also, you look at the power consumption. If you have enough power on the circuit to power that particular mode of protocol or not. So also you have to look at the complexity. How complex is it for you to set up? Sometimes it might be difficult to set up Zigbee compared to Bluetooth. And sometimes it might also be difficult to set up SPI compared to I2C. So you have to look at all these protocols and look at the one that will give you the best return or that make things much more easier for you. So that's basically it on how our devices communicate, and also on the principle of embedded system. There are other things that are involved in the principle of embedded systems and electronics. You can always learn more on this online and search for anything. And if you have any other question, you can always ask in the comment section below. So lastly, we are going to move into the last part, which is we're going to be streamlining down to the sensor that we're going to be using, which is Arduino Nano 33 BLE sense, throughout this tutorial. So as I said, we are going to be comparing the Arduino Nano 33 BLE sense and the Raspberry Pi Pico, which will be the two major boards that I'll be using all through the series. And here we have the Arduino Nano 33 BLE sense board. It's designed by Arduino, as you might have guessed. So it's combined microcontroller RP2040 powered by an ARM Cortex M4 processor with several sensors and Bluetooth radio for an easy TinyML integration and development. So you're going to be looking later at each of these sensors that the Nano 33 BLE sense come with, and now you can use each of those sensors. And here we have the Raspberry Pi Pico. It's designed by Raspberry Pi Foundation. So it does not provide sensors and the Bluetooth module on board like the Arduino Nano license. So it has a microcontroller RP2040 powered by dual-core ARM Cortex-M0 Plus processor for unique and powerful TinyML application. So each of them has different ways we can use it. We can use them. I'm going to be looking at these two different categories. Now let's streamline down to the Nano 33BL license. As I mentioned earlier, that we have a lot of boards, a lot of modules that are on board the sensor. So let's look at each of these modules and where they're located with a pictorial representation on the board. So we have the full board here showing the full length of the board. So we have the chip, which is the controller, NRF52840 as the MCU unit on the board, and it's located just at the right hand corner. So we have the HTS221 temperature sensor. The location is marked with the red box. Also, we have the barometric pressure, which is LSP22 sensor. So the location is marked also. If you have the board with you, you can follow along and check for each of these sensors. Also, we have the microphone. It comes with a digital microphone. It is MP34DT06J. So we also have the gyroscope sensor, accelerometer sensor, and the magnetometer sensor, which is LSM9DS1. And lastly, on the board, we have the proximity sensor, ambient sensor, light sensor, RGB, and gesture sensor, which is APD S9960. So the location is marked with the red box. So as we round off the tutorial, let's do a quick comparison of the Raspberry Pi Pico and the Arduino Nano 33BL license. As you have on the screen, I have a simple schematic of the two of these boards. As you can see, the Nano 33BL license contain different sensors. But if you look at the Raspberry Pi Pico, the only thing you have there is the chip. There are no any form of onboard sensor or anything. So as you can see from the side-by-side comparison, they both have incredibly small form factor, a USB port for power and also for programming, and they are both ARM-based microcontroller. So at the same time, they have unique features that make the board ideal for targeting TinyML development scenarios. So that's basically it. You can check more and read more on Nano 33BL license and also on Raspberry Pi Pico. So from the beginning of this tutorial, we've looked at the review of machine learning, we've looked at the review of electronics and embedded systems. We have done with basically everything that we need to look at as for preliminary studies. In next tutorial, we're going to go fully and start developing using our boards, using Nano 33BL license and using the board RP2040. So if you find this tutorial useful, don't forget to give it a thumbs up, like, and share. And don't forget to subscribe for you to be updated with latest tutorials that will be coming up in this series. So thank you so much for watching this tutorial up to this end, and I'll see you in the next tutorial. Thank you.